Hi. To solve linear systems, we were using echelon form and elementary matrix operations so far. Would not it be convenient if we could just divide by matrix A like we do with numbers? Unfortunately, dividing by matrix is not defined. However, the concept of A in the power minus 1 exists. It is called inverse of a matrix. Let us first start with normal numbers. If you have an equation ax equals b and want to solve it for x, you can multiply the equation with the multiplicative inverse of a, which is 1 over a, or a to the power minus 1. The inverse has the properties 1 over a times a equals 1, and a times 1 over a equals 1. For square matrices, we take the same approach as for the numbers. A square n by n matrix A is called invertible if there is an n by n matrix C such that C times A equals In, and A times C equals In, identity matrix of a size n. If C exists, it is unique, so we can call C the inverse of A and denote this by A to the power minus 1. Just like for the numbers. If C does not exist, you say A is singular. Let us try the example together. The matrix A is 2, 5, minus 3, minus 7. And the matrix C is minus 7, minus 5, 3, 2. We can calculate A times C, which gives us 1, 0, 0, 1, which is the 2 by 2 identity matrix. Calculating C times A again gives us the identity matrix also. So according to the definition of the inverse, A is invertible and the inverse of A is C. Now, take a closer look at A and its inverse. You can see that the inverse contains almost the same numbers as A. On the diagonal, the 2 and the minus 7 have switched places, while all the other numbers are multiplied by minus 1. Is that a coincidence? Let's try to apply the principle of this guess to general 2 by 2 matrices. With A given by A, B, C, D, and C by D minus B minus C, A. We can do the multiplication of C and A and arrive at the diagonal matrix with A times D minus B times C on the diagonal. You could however multiply C by the scalar 1 over A times D minus B times C to get A in the power minus 1, which will give you the identity matrix if you calculate A in the power minus 1 times A. In this case, you even get the identity matrix if you calculate A times A in the power minus 1. You can check this result yourself. Now we have found the inverse of A, and so A is invertible. You should however remember that we made an assumption that A times D minus B times C is unequal to 0, because you divided by this number. You should recognize this number. A times D minus B times C is the determinant of A. Now you know when a 2 by 2 matrix has an inverse. Now we know that if 2 by 2 matrix is invertible, the inverse can be found by the formula on the slide, and the quantity AD minus BC should not be equal to 0 if AD minus BC, the determinant of A, is equal to 0, the matrix is called singular. Still, the question remains, why elements A, B, C, and D in the inverse take their particular places with particular minus signs? Turns out that the inverse of matrix A can be calculated as following. This expression is called Cramer's formula and is applicable for all invertible square matrices. C, G, I are cofactors of A. Note that the ij entry of matrix A in the power minus 1 is the cofactor Cji, not Cij. Cofactors are familiar to you already as a tool for calculating determinants. Now you can also apply them for finding the inverse. Let's check that this formula actually works for 2 by 2 matrices. The element of matrix A with the index 1, 1 is A. It is the same as a cofactor C22 of the matrix A. Check with the lecture about determinants on how to calculate cofactors. With the same logic, the element A12 of the matrix A is a cofactor C21 of the matrix A with a minus sign. Remember that the cofactors have a signed plus or minus sign in their value. The same goes for the element A21 and for the element 22 of matrix A. That is an explanation of how the elements of matrix A switch places and signs in the formula for the inverse. In class, you will discover how to apply Cramer's rule for the n by n matrix and other ways of finding the inverse of the matrix. Hope you enjoyed this video and see you in class.